Hi everyone, today we're going to talk about how do we solve a linear programming model. Once you have a linear programming model built, you must be thinking about how do we get the solution. Or when you see the solver runs and gives you a solution, have you ever wondered how those decision variable values come? So today we're going to talk about 3 different methods that can be used to solve LP models. The first one is a graphical solution. So the graphical solution method can be used when we have only 2 decision variables. So you can plot them on the coordinate system and find out the optimal solution on that coordinate system graph. And the second approach called the heuristic approach. This is a rule of thumb method that people use to solve some simple models. For example, the newspaper ads and the TV ads problem we talked about last time. We did try to solve it by thinking about how the problem would solve and how do you get the optimal objective function value and while at the same time satisfy the constraints. Heuristic approach sometimes is the only way to solve some complex models, and we'll talk about that in details later. The third method, the simplex algorithm. This is the algorithm underlying those softwares that we use. For example, solver. When we solve those LP models, we said you need to set your method to the LP simplex. And that's the algorithm that the solver uses to calculate the decision variable values and also the objective function value. So first, let's look at the Blue Ridge hot tub problem. So once we had this model for this problem, if you recall, we have 2 decision variables. The objective function is a linear combination of the unit profit and our decision variables representing the number of the 2 types of hot tubs to manufacture. Okay, and the constraints, we have 3 of them, each representing the resources to be used by producing the 2 types of hot tubs need to be less than equal to the resources available. And we also have the non-negativity constraints. So to solve this model, an intuitive approach would be to think about because each equals bus generates the highest unit profit, which is $350 as compared to the $300 of hydrolysis. So let's just make as many of them as possible. So how many would that be? If we just use up all the resources to make equals bus, then we would just let x2, which represents the number of hydrolysis to make, to be 0. And then using the first constraint, we would get x1 less than equal to 200. And using the second constraint, we would get x1 less than equal to 174. And using the third constraint, we would get x1 need to be less than equal to 240. Okay, so now combining these 3 constraints, the maximum of x1 value that can be is 174. So that would give us x1 value. And if we plot this x1 value to the objective function, we would get $60,900 as the objective function value, which is the total profit. And because we set x2 value to be 0, so that's why this part is 0. We don't make any profit from the second type of hot tub. This solution is a feasible solution, which means that it satisfies all the constraints. In fact, that's how we get our x1 value, right? So we look at if we set x2 to be 0, what would be our x1 value using all the 3 constraints? So this x1 being 174 and x2 being 0 is a feasible solution to our model that satisfies all the constraints. But is it the optimal solution? Is this total profit that we get the maximum value that we can have from the model? The answer is no. As we solved it using solver, we know that our objective function value is much higher than this. Okay, so that means this is not optimal. So there must be a combination that gives us a better objective function, which is a better total profit than just producing the equal spots that makes the most unit profit. Okay, so let's talk about how do we solve this problem using a graphical approach. So the constraint of an LP model defines the feasible region of the solutions. What does that mean? The constraints, when you combine them together, it gives you a region in which all the points in that region will be a feasible solution to our problem. So a point that satisfies all those constraints will be considered a feasible solution to the problem. And all those points putting together represent the feasible region of the problem. And the best point in this feasible region is the optimal solution to this problem. So when we look at this feasible region that contains all the points or all the solutions that satisfy the constraints, then we would like to pick a point or points that would give you the best objective function. And that point or points would be the optimal solution to the problem. For LP problems with two decision variables, it's easy to plot that feasible region and find that optimal solution. And let's look at how do we do that. So we're going to look at first the feasible region of this problem. I have the model here for our reference. And let's look at the first constraint. The first constraint is x1 plus x2 less than or equal to 200. So if we just draw a coordinate system with our two decision variables, x1 and x2, one on each axis, it doesn't matter which one you put. You can put x1 on the vertical one or the horizontal one. It doesn't matter. Okay. And here we put x1 on the horizontal one and x2 on the vertical one. And then for x1, x2 less than or equal to 200, we would first convert this constraint into an equation. Okay, so instead of having less than or equal to, let's just put it as equation. And then we'll find out the 2 points that define this line. And if we look at setting x1 to 0, what will be the x2 value? And then setting x2 to 0, what will be x1 value? So if we do x1 equal to 0, okay, and then we know that x2 would be 200. If we set x2 to be 0, then x1 will be 200. So we identify those 2 points. One is 0, 200. Another point is 200, 0. Then we would connect these 2 points to find that line that represents the first boundary line of the pump constraint, which represents x1 plus x2 equals to 200. Okay, so note we did that by identifying the 2 points first by setting one of the variable to 0 and find the other variable's value. And we plot this line like here. So this is the boundary line of the first constraint when we change it to an equation. Then what about representing x1 plus x2 less than or equal to 200? We would shade the area under it. Okay, so because we also have this x1, x2 greater than or equal to 0, so this blue area that gets shaded represents the constraints with the non-negativity conditions added. Okay, otherwise it would be, if we don't have those non-negativity constraints, then it would be the entire area under this line here. Okay, now let's look at the next constraint. We're going to do the same thing. we're going to first convert it to an equation. So we'll have 9x1 plus 6x2 equals to 1566. And using that equation, we're going to draw a line representing that equation. So first set your x1 to be 0 and calculate your x2 value. Then set your x2 to be 0 and calculate your x1 value. So if we set x1 to be 0, then we get 6x2 equals to 1566, right? And then 6x2 would equals to be 1566 divided by 2. So that's our first point, which is 0, 2, 6, 1. So x1 is 0 here, and x2 is 261. That's one first point, okay? And then we're going to set x2 to be 0. x2 to be 0 here, we're going to find out on the horizontal axis where the point is. So if set x2 to be 0, then we have 9x1 equals to be 1566. Now x1 equals to be 1566 divided by 9, which is 174. So 174, 0 is the second point that we get to draw that line. So we connect these 2 points. We get this second line here that represents the second boundary line of the labor constraints. And it's the 9x1 plus 6x2 equal to 1566. Similarly, we're going to find out what's the area that represents the 961 plus 6x2 less than equal to 1566. We would shade the area under this line here, okay? And because our feasible region should satisfy all the constraints, we've already got the feasible region for the first constraint, which is shaded in blue here. Then now adding this additional constraint would be the area that overlaps. Okay, so this red one overlap with this blue one, which gives us this area. So you can see, once we add one more constraint, our feasible region shrinked. Okay, originally it had this entire area. Now this small blue area, this small part, was excluded from our feasible region. And our feasible region now becomes this yellow shaded area. Then we're going to do the same thing. We're going to add our third constraint to our graph. And so first step, change this to an equation. 12x1 plus 16x2 equal to 2880. And once we change it to an equation, we would be able to plot it on the coordinate system by finding out 2 points. And we do that by setting, so that's the easiest way. Okay, we can set x1 to be 0, find out what's the x2 value, and set x2 to be 0 to find out the x1 value. So when x1 is 0, x2 equals to be 2880 divided by 16, which is 180. Okay, so that's the first point we get. It's 0, 180. And then we're going to set x2 to be 0 to calculate x1 value. x1 equals to be 2880 divided by 12, which is 240. So we find that the second point is 240, 0. It's somewhere here. Now we connect these 2 points. We've got the third line that represents the boundary line of the tubing constraint. And so once we had this line here representing this equation, we're going to find out the area that represents our constraint, which is 12x1 plus 16x2 less than equal to 2880. So since it's less than equal to constraint, we're going to again shade the area under it. So it would be something like this. Okay, so that's the area under this line here. Now to find out our new feasible region that satisfies all those constraints, it needs to be the one that overlap with the previous one. So the previous one was shaded in orange. Then we would know that, okay, the overlapping part is something like this. Okay. So it's this area here. And you can see that the final feasible region starts from this point here and go all the way to this point here and went to here, and here. So this is our feasible region that satisfies all those 5 constraints. Okay. So we call this the feasible region. Again, that means all the points. So you pick any points in this region. Some on the edge, some on the corner. So any point in this region would be a feasible solution to our problem, meaning that any point here satisfies all those 5 constraints we have. Now, with the feasible region identified, our purpose is to identify which point that gives us the maximized objective function value. Our objective is 250x1 plus 300x2, and then we want to find the maximized value of it. How do we do that? We only know that all the points can be a feasible solution to our problem, but which point would give us the maximized value, that is 350x1 plus 300x2? How do we do that? How do we find a point or some points that maximize this value here? Can you think about it? So now let's look at how do we identify that point in this feasible region that gives us this maximized 350x1 plus 300x2 value. Let's just assume that our objective function is z, okay? We're going to maximize this z that equals to 350x1 plus 300x2. Then let's find out what this z value is, or where this z is on this coordinate system. Since our coordinate system was drawn using x1 and x2, and x2 is on the vertical axis, then let's just move x1 to the other side. We would get 3x2 equals to this z subtract 350x1. Okay, and then let's divide the 300 on both sides. We would get x2 equals to be z divided by 300 subtract 350 divided by 300 multiply x1. Now we changed our objective function into this format. That's the standard format when we try to represent x2 on in this coordinate system. So x2 is on the vertical side, and it equals to be this value subtract another numerical value multiply our x1. Now the question, where is this z divided by 300 on this coordinate system? What does it represent? If we want to draw it on this coordinate system, where do we draw it? Or what does it represent? What does this z divided by 300 represent in this coordinate system? Please think about it. So we know that with x1 and x2, with some coefficient, we can draw them. Just like how we draw those constraints, converting them to equations, we draw some lines in this coordinate system, right? And this is another equation of x2 that we can draw some lines. okay? And the only thing that we don't know what our z is. So let's use this to continue, okay? If we want to draw some lines, we know that the slope of those lines using this equation here is this negative 350 divided by 300, which is negative 76 or negative 1.1667. So this part is our slope. Then what about, let's just start to draw some lines, okay? We know the slope is negative 7/6 or negative 1.166. So we just pick one point. For example, let's just pick a point of x1 being 100 and x2 being 0. So this is 1 point. Using this slope, we would be able to identify that the other point is 0.11667 because that's our slope. Okay, so when our x1 is this part, when our x1 is 100, using a slope of negative 1.1667, our x2 would be here. So would be 116. And we can draw a line that has a slope of negative 1.1667. So that's one line that we can draw using the slope from this equation here. Then where is our z divided by 300? This is the intercept on our x2 coordinates, right? So that would be this part here. And that gives us an objective function that the value equals to be 35,000. Okay, and this part is our z divided by 300. And our z value equals to be 35,000. So if you use 35,000 divided by 300, you would get this value here, which is the intercept on our x2 axis. Then if we just want to draw any line using this equation here, we can just find out, the easiest way to find out to draw one line would be to start from, because the slope is negative 7.6. The easiest point will be 60, okay? You start from 60, and then your x2 value would be 70, right? Because it's negative 7/6. So that's another line we can draw with exactly the same slope, which is negative 1.166. And these two lines would be parallel. We call those lines that we draw using this same slope defined in this objective function as level curves. Okay, so we can keep using this same slope to draw different lines that share the same slope. For example, the first one we draw has an objective function of 35,000. And if we identify a second line, for example, 0.0175 and the 0.150, that has the same slope of negative 1.1667. That's another line. And that would give us another objective function, which is 52,500. And you notice that when we go from this first level curve to the next level curve, our objective function value increased from 35,000 to this current value. And we can keep going, pushing outwards in this direction, and then we get another line that has the same slope, but gives us the optimal solution at this point here. Okay, and at this point, we can see that the intercept on this x2 axis, which is our z divided by 300, if you recall. That gives us the maximized z divided by 300 value. The reason why this is our maximized z divided by 300 value is because this current line already is just touching one corner point of this feasible region. Okay, if we keep pushing it outwards, our intercept on this x2 axis, which represent this z divided by 300 value, can keep increasing. However, since we're going out of our feasible region, then whatever point we identify is no longer a feasible solution to our problem, which means that the constraints won't be satisfied. So to find out that optimal solution, we need to satisfy two conditions. One is that the point need to be within this feasible region. Okay, like this corner point, it is right on the edge, right on the corner, but it is still within that feasible region. And the second condition is that it gives us the optimal objective function value. And in this case, is the maximized objective function value, the maximized z value. So as long as we maximize this z divided by 300, we are maximize our z value, right? So this is our optimal solution that we can identify using this level curve method. And to calculate this optimal solution, because now we know that the optimal solution occurred at this corner point here. And this is where the pump and the labor constraint intersect. Recall that when we draw this feasible region, this point came after we draw this second line representing the second constraint, when we already had the first line here. So how do we identify this point? Because we had two lines that intersect at this one point, which was identified as our optimal solution, we should be able to find out the x1, x2 values by changing these two equations and solve them. Okay, so this occurs where the x1 plus x2 equals to 200 and this one. So when we solve those two equations, we can do it the same way. So from 1, we can get x2 equals to 200 subtract x1, and substituting this 3 here for x2 in this 2 equation, we can get this part, which reduces to x1 equals to 122. So you should be able to solve the equations. Okay, and so the optimal solution is x1 equals to be 122 and x2 equals to be 200 subtract x1, right? Subtract 122 gives us a 78. So this is our optimal solution. x1 equals to be 122 and x2 equals to be 78. And when we plug those two values back to our objective function, then we would be able to get the optimal objective function value, which is the total profit that equals to be $66,100. And remember that if we only produce aqueous bus and not producing hydrolysis, we get about $65,000, which is lower than this value. So now we find that a perfect combination of the x1 and x2 value that gives us the maximized objective function value. Some common problems that you may meet when you use the graphical method to find out solutions is that, first, do I shade the area above or under the line drawn using the constraints? So when you do this, you want to first make sure that the sign of the decision variable that is on the vertical axis is positive in your constraint. Okay, for example, in that graphical method we just went through, in that problem, we put x2 on the vertical axis. for less than equal to constraint, we shaded the area under, and for greater than equal to constraint, we shaded the area above. That's because all the x2 in our constraints are having positive coefficients. And if you have a constraint in which that decision variable on your vertical axis has negative signs, then you would either do shading the area opposite way. So less than equal to would be shading above, and the greater than equal to would be shading area under. Or what I usually do is that I convert that constraint first. Okay, I multiply a -1 on both sides if my decision variable has a negative coefficient, and that would change the direction of the greater than equal to less than equal to sign when you multiply a negative on both sides of that constraint, and to make sure that the decision variable that's on the vertical axis need to be positive. Then with that, you would shade the area under for less than equal to constraints, and shade the area above for greater than equal to constraints. When you are in doubt, use 0.00 to double check. Okay, I'll illustrate what I mean here. For example, when we plot those constraints, you see my x2, which is on the vertical axis, they all have positive signs. So for those 3 constraints that are less than equal to, we shaded the area under that line. And we can use a 0 point just to double check. Take this second constraint for example. If we want to know whether I shade the area under this line or above this line on this side, let's check if 0 satisfies it. Okay, so you put the 0 to this equation. So 0 is less than equal to 1566, which means 0.00 satisfies this constraint. So 0.00 should be included in that area you shade. So what does that mean? You would shade under this line here, so that 0 is one of the points in that area you shade. Okay, but if 0 does not, when you put the 0 in your constraint, it does not satisfy the constraint, then that means you should not shade the area under. That includes the 0 point. You should shade the area above it. How about 20x1 take away 10x2 less than equal to 1000? How would you do this one? So we can draw the line here, okay? So I'm going to insert a line. So first find out the 2 points. So my x1 when it is 0, my x2 value is what? When this is 0, my x2 is -100, right? It's somewhere. x2 is -100. Would it be somewhere here? And when my x2 is 0, my x1 is 50. So 50, x1 is 50. So it will be a point. When your x2 is 0, your x1 is 50. And something like this. So the line would be something like this. Okay, so my other point is when x1 is 0, my x2 is -100. So that's why my line is something like this. Okay, so when you have this constraint, you remember that we draw it in a way that it's 20x1 minus 10x2 equal to 1000. Should we shade the area above it or under it? This was the line that we draw, okay? And first of all, this is a negative. Even though this is a less than constraint, we don't want to shade the area above it. So we won't shade in this way, okay? even though it's less than equal to constraint, because our x2, which is on the vertical axis, has a negative coefficient. So if we change the sign, it would be 10x2 subtract 20x1 greater than equal to negative 1000. So it will be changed to a greater than equal to constraint. So actually we should shade above this area here. We would not shade under it, even though it's less than equal to constraint. Now, if we are in doubt, we can use this 0, point to test if we shaded this area correctly. Okay, now we shaded this area and 0, is within it, which means that 0, should satisfy our constraint. So if we put 0 here and 0 here, we get 0, less than equal to 1000, which is correct. Okay, so 0 is less than 1000. That means my point 0, satisfies this constraint. It should be included in our feasible region. And since we shaded our feasible region in this way, then we double check and it confirms the area we shaded is correct. So if you shaded under it, you would see 0, is not included in your feasible region that you shade, which is wrong, because 0, should be included. So that's the first thing we want to talk about. The first common problem, not being sure of which area you shade, is that above the line or under the line. Another common problem that people meet is that once I identify the first level curve, in which direction should I move it to find the optimal solution point? If you remember, once we had that objective function change to the way that we move the decision variable that's on the vertical axis to one side and the rest of the function to the other side, we would use the slope of that function to identify several curves. That's called the level curve. So once I have my first level curve, should I move outward or should I move inward to identify my optimal solution? That depends on your objective function. Okay, in our example, it's to maximize the objective function value. So we moved outwards to increase that intercept on our x2 axis. And if it's a minimization problem, then you would move inward for that problem to minimize the intercept on your x2 axis. So whether to move outward or inward really depends on if it's going to improve your objective function. If it's a maximization, then you want to increase it. If it's a minimization, then you want to decrease it. And here's one concept that I like to introduce. The gradient is a fancy word for derivative, or the rate of change of a function. And it is just a vector like this. And this gradient is a direction. Okay, it has no starting points. In optimization problems, we would follow this trajectory to reach a corner point and then check the gradient again. Be careful not to confuse the coordinates and the gradient. The coordinates are the current location, so your x1, x2 value, and measured on those axes. And the gradient is a direction to move from our current location, such as move up, down, left, or right. And once we know this concept of a gradient, we're going to use it to identify which way to move once we have our level curve. So the gradient vector is always perpendicular to your level curve. If we identified our level curve, so this red line here is our level curve, the gradient is perpendicular. And which direction should we move depends on your x1, x2, or in this case, it's x and y coefficients. Okay, so if your your both decision variables have positive coefficients, then we are in this quadrant here. And then we would move in this direction here. our gradient is a 1, 1. They're both coefficient. Okay, so we will move in this direction. Using our example here, we had this one level curve identified first. And because our gradient vector is 350 and 300, they are both positive. Okay, so they are in this quadrant, and then we would move in this direction here. And because it's a maximization problem, so it's a maximization problem, we would move in the direction of the gradient vector. And we find our optimal solution when we keep moving in this direction and touch one of the corner points of our feasible region. And if we keep moving outwards, we would go outside our feasible region. Then if it's a maximization problem, then we would move in the opposite direction of the gradient vector. So if this is a minimization problem, we would move this way. And optimal solution would be coming to here, will be 0, 0. Okay, and so if the problem was minimize the 350x1 or plus 300x2, we would go in this opposite direction and end up at this 0, 0 point. Another example. When we have the two decision variables in the objective function, one of them, the first one, okay, the one on the horizontal axis, is having a negative coefficient, then our vector is negative, positive, and it will come this quadrant, and the direction would be going here, like this. That's your gradient vector direction, okay? And if you have the coefficient of your decision variables being positive, negative, then you would go to this quadrant, and the direction of moving would be this way, the vector, gradient vector. Lastly, if both decision variables, the coefficients are negative, then you would come to this last quadrant, and the gradient vector direction would be going to this direction. And you would move, if it's a maximization problem, you would move in the same direction of your gradient vector. And if your problem is a minimization problem, then you would move in the opposite direction of those gradient vector. So depending on the coefficients signs of your two decision variable coefficients, you would decide the direction based on that gradient vector, and if the problem is a maximization problem or minimization problem. Okay, so let's summarize. Using the graphical method to solve LP problems, the first is we plot those boundary lines of each constraint. We change all those less than equal to constraints and greater than equal to constraints into equations, so we can draw lines based on the equations. Next, we identify the feasible region. So the feasible region would be the area that either under or above the line that you draw. And we talked about earlier, if the easiest way to make sure that the variable that's on the vertical axis is positive in your constraint, and you would modify it if necessary. For less than equal to constraint, you shade the area under, and for greater than equal to constraint, you shade the area above. And when you are in doubt, use the 0.00 to test to see if the shaded area is correct. Locate the optimal solution by either using the method we talk about, plotting level curves. So you would identify the slope of your level curves using the objective function, and then move your line in the direction that helps improve your objective function value. Move it in the direction of the gradient vector of the objective function if it's maximization problems, or if it's a minimization problems, move in the opposite way. Okay, and the next method we can use is called enumerating the extreme points. So when we solve that problem, we find that our optimal solution is at this point. It is one of the corner points of this feasible region. Okay, if you think about it, when you draw the level curves, we keep moving it in a certain direction. When that level curve touch one of the corner points, then we identify the optimal solution. The reason why we would enumerating corner points is that we know our optimal solution would always occur on the corner point. And that corner point represents the extreme points in your feasible region, where if you move a little bit further away, then you will be out of that feasible region. So those corner points would be, one of the corner points would be giving you the optimal solution. Knowing that, we can instead just look at all the different corner points and then calculate the objective function value that those points would give you. So you would plug in those values. So for example, this point here is the 0, 1, 80 point, and you would plug these two values into your objective function to calculate what the value is. And the same for those points. And you would be identify those points by using those constraints that define the feasible region, right? So this would be the constraint that is x1 greater than or equal to 0, and the first constraint, x1 plus x2 less than or equal to 200. And this point would be, say, the first constraint and the third constraint, and so on. So you would first identify all those corner points by calculating their x1, x2 values, and then plug the x2, x1 values into your objective function to find out what the objective function value is. Then you compare them. Say the first one is 54,000, 64,000, 66,100, 60,900. So you would identify this to be the optimal solution point because it gives you the maximized objective function value. Okay, so this is one method that we can use in addition to that level curve method to identify the optimal solution. And note, this method will not work if the solution is unbounded, which means that it has no one area is not bounded by those constraints, so you can keep going in that one direction without touching any corner points. So if there's no corner points in that direction, then you would not be able to enumerate the corner points. We're going to talk about more about this unbounded condition. Okay, and another method is to combine the level curve and enumerating corner point method together when you are in doubt. For example, sometimes there could be some corner points very close to each other. Like for example here, we know that this was our optimal solution point that we identified when we draw this level curve. And when you draw the level curve, especially if you can't really draw it true to scale, it can be really hard to tell whether it's this point or say this point, or sometimes you would be think about whether it's this point or this point, because they have really slight difference between this intercept, these two intercepts here. Okay, especially if you are not drawing true to scale, it can be really hard to tell between these 2 points or this and this point. So when it's hard to tell, and when you doubt if you really draw it true to scale, then you can identify the objective function value given by these 2 points and compare them. Okay, compare them and then find, okay, this is the better one, or include this point too. So you would identify these 3 points and see which one gives you the highest objective function value. Usually, there are some corner points, for example, this one, they are more obvious that they are not the optimal solution points. but it's only like these 3 points because they are really close in terms of the slope of the level curve and that constraints that defines that edge of the feasible region. So it can be hard to really determine which point it is. Then just calculate the objective function values for those 2 points and choose the one that's better. Okay, like in this case, this is the optimal one. So with this, we are done with the graphical method to solve LP problems.